DBMS stands for Database Management System. It's a software system which helps in managing incoming data, organizing it, and providing certain ways for the data to be modified or extracted by the users or other programs. Relational databases are made up of relations, commonly known as tables, because the relationship exists between these set of tables. For example, we have a database called city and it has some set of tables here. Each table has some columns. Here login, I'm showing login table. It has unique name. Each column has an associated data type. Columns are sometimes called as fields or attributes. Now rows. Each row in the table represents different employees in this case. Rows are also called as records or tuples. Now each row has certain values. Every value must have the same data type as specified by its column. Here name has varchar, phone number is integer type, etc. Key. To identify each person or thing uniquely in a table, that is each row uniquely, we need some unique value. Schema, complete set of table design for a database. It's like a blueprint for the database. A schema should show tables along with their columns and some data if possible, and its primary key of each table and foreign key, etc. Usually primary keys are underlined and foreign keys are italicized. There comes some problem called anomalies. If you don't do the normalization process properly, that is division of data into different data table sets. We will explain that in coming tutorials in detail with examples. For now, let's see about anomalies. Think we have some online store and somebody is ordering it. A person called Satish orders one item. Second time when he orders, he is moved to different place. This is insertion anomaly. If we try to edit the address at one place, there is inconsistent data, so that is modification anomaly. If once the order is delivered, we delete the data and the address is no more present, that is deletion anomaly. To solve that, we have primary and foreign key. We store name and address in one place and use a primary key called username, for example, and we refer to this column in all other table, hence solving the problem. This is called normalization, and there are certain things like one-to-one relationship, one-to-many relationship, and many-to-many relationship. Well, that would get complicated for now, so we will explain each one of these in coming video tutorials with some real-time examples. So hope you understood what is some of the basics of database management system. That is, each database has certain number of tables, and each table, most of the time each tables have some relationship between them, and most of the time every table has a unique key, that is primary key, to identify each row uniquely, which helps in normalization process in most of the cases. And if we don't do normalization properly, that is, we don't have that skill, that art of dividing the data into different tables, we face anomalies, that is insertion anomaly, modification anomaly, and deletion anomaly. So for now, just know these things: database, tables, columns, rows, values, keys, foreign key and primary key, and these anomalies. These are some of the basics to get started. And for these definitions and other detailed notes about all these terms, please visit the link present in the description section of this YouTube video. Please share this video with your friends on Facebook, Google+, Twitter, LinkedIn, etc. And please make sure to like this video on YouTube. Also, please subscribe to our website technotip.com. Thank you.
Oh boy, that's a really tough question. It's kind of like asking, what are the 5 countries you should know about if you're not interested in geology or geography or politics? Um, and the answer varies depending on what your actual interests are, or what are the 5 companies you should know. Uh, but and the answer changes over time too. Back when I was getting started, these many decades ago, the answers would have been Fortran, COBOL, BASIC, Lisp, and maybe APL. And those were very formative languages back then, and people learned a lot from those. But these days, it might be more important for you to know JavaScript, even if the only reason you know that is that you know whether or not to click the Enable JavaScript button in your browser. But JavaScript is a nice, lightweight, object-oriented language. And that's why it can fit in a browser and do these things such as run little programs that help you input your data and then send it off to a web server somewhere. There are heavier weight object-oriented languages, and the elephant in the room is sort of Java. You can't really make a list of modern languages without talking about it. Java is sort of the COBOL of the 21st century, I think. It's kind of heavyweight, verbose, and everyone loves to hate it, though not everyone will admit that. But managers kind of like it because it looks like you're getting a lot done. If 100 lines of Java code accomplish a task, then it looks like you've written 100 lines, even though in a different language it might only take 5 lines. It's like you can eat a 1-pound steak, or you can eat 100 pounds of shoe leather, and you feel a greater sense of accomplishment after the shoe leather. But maybe there's some downsides. But it also because it is sort of considered an industrial language and programmers are sort of interchangeable parts, managers like it for that reason, and for that reason a lot of Java jobs have been outsourced from the United States. What other languages? I think going in a different direction, coming more from academia, we have a language like Haskell, which we call a functional programming language. That means function in a mathematical sense, not in the sense that other languages are dysfunctional. But a function mathematically has an input and an output, and it maps to with a great deal of mathematical certainty what those are. So Haskell is one of those languages that mathematician-type-minded people love. It's sort of a language for geniuses, by geniuses. So you should probably know about it, if only to be able to say, well, is this kind of like Haskell? And if so, then you have to hire some really smart people to program in it. Haskell is sort of a modern kind of Lisp in that sense. What else? Well, we can't leave off modern languages without talking about C. The C language, that's just spelled with the letter C, is actually about 40 years old, but people have tried to replace C with other languages that are like it and have, by and large, not succeeded because C is a very minimalistic language and very close to the metal, as we say, on a machine, and lets you get down and do very fine-grained stuff very efficiently, but it's a lot of hard work. But once you've done that work, you can run it pretty much everywhere. So almost all the other languages that you see, Java, Perl, whatever, actually, if you look down underneath, they're actually implemented in C or in a closely related language. So that continues to be a very fundamental language, if only because everyone is trying to reinvent it and not succeeding in doing so. And finally, for a fifth language, well, you'd probably want to pick one of the scripting languages. There's several to choose from. There's Python, there's Ruby, but of course I am prejudiced in favor of Perl because I think it has the liveliest community, and because we have intentionally been redesigning it lately to leapfrog all the other languages. For the last number of years, we've been redesigning it to take out all the warts that we've noticed over time. And we figured it was just our one chance to break backward compatibility, break the things that need breaking, keep all the things that make Perl, keep it a joy to use, and with this redesign, make it a language that will be able to be useful and enjoyable for decades. And so I'd recommend Perl, but I'm known to be prejudiced in the matter.
In the early days of computing, there was a language barrier between computers and humans because you had to use machine language if you wanted to talk to the computer, either in binary code or its exact English equivalent. This was very slow and laborious. Every time a generalist wanted to tell the computer to print something, or make a decision, or repeat an operation, he had to break every statement down into tiny electronic steps. The same for the mathematician who had to translate all his math symbols into long-winded computer talk. And even the businessman who just wanted to do payrolls and inventories and make out bills to his customers had to spell everything out in nitpicking machine language. But eventually, after a number of years, people began to realize that they were translating the same fundamental ideas into machine language over and over again. So they made lists of the instructions and symbols and procedures that each of them used most frequently, and they called these lists high-level languages. For example, BASIC for generalists, APL for mathematicians, and COBOL for businessmen. And then they prepared automatic dictionaries, which, just like English-French dictionaries, contained a list of all the vocabulary of the particular high-level language in one column with its machine language equivalent in a second column. Then, whenever someone wanted to use a key word or symbol or procedure in the high-level language, this dictionary would look it up, find out what it meant in machine language, and pass this on to the computer. These dictionaries, which automatically translated from a high-level program into a low-level machine language program, were in fact themselves programs, translator programs. And as soon as translator programs came into existence, people no longer had to speak machine language if they didn't want to. They could speak much more convenient languages such as BASIC or APL or COBOL or Fortran or Lisp or Pascal or Forth or any of hundreds of other specialized high-level languages that have developed over the years. The language barrier between computers and humans had broken down.